Hello and welcome. Today we dive into the deadly skies over Western Germany in February of 1945, where a single technological breakthrough was rewriting the rules of aerial combat, one that would claim the lives of dozens of Luftwaffe pilots and turn the battlefield into a brutal contest of control and speed. Have you ever wondered how a seemingly simple mechanical device could suddenly make a fighter jet uncontrollable at hundreds of miles per hour? How did the British manage to outmaneuver the Germans, not just with tactics, but with innovations that shattered aerodynamics? What was this mysterious spring tab system that transformed the Hawker Tempest into a high-speed predator, yet rendered German fighters nearly helpless? Could a tiny mechanical adjustment really turn the laws of physics against the Luftwaffe's best pilots? And most chillingly, was this technological edge so devastating that it changed the course of the air war itself, turning skill and bravery into a deadly game of mechanical advantage? In this video, we will trace the origins of this deadly innovation, expose the German pilots' struggle against forces they couldn't see, and reveal how one seemingly minor mechanical device altered the fate of countless lives. The story begins right now. Uncover the shocking truth behind the skies of 1945. In the waning days of the Second World War, specifically on a cold February morning in the year 1945, a dramatic aerial confrontation unfolded over the skies of Western Germany. The clock had just struck 400 hours when Lieutenant Heinrich Roth, a seasoned pilot of the famous Jagdgeschwader 26, found himself locked in a deathly dance with an enemy fighter. His hands clenched the control stick with determined force, pushing it sharply to the right at a velocity of 400 miles per hour. An incredible speed that taxed both his muscles and his aircraft's limits. Despite his vigorous effort, he could feel his arm muscles burning painfully, yet the control stick responded with only the tiniest of movements, a mere centimeter at best, almost as if welded in place by some unseen force. He knew with certainty, sharpened by the relentless logic of his training and experience, that he was perilously close to disaster. The aircraft he was commanding, a formidable Focke-Wulf FW-190, was refusing to respond as it normally would, its control surfaces seemingly frozen amidst the chaos of high-velocity flight. Behind him, the British opponent, the Hawker Tempest, moved with an almost effortless grace. Its 420-millimeter cannons tracked steadily toward his cockpit, their deadly projectiles ready to strike. The control stick, so vital for maneuvering, felt as if it had been welded to his hand, requiring over 60 pounds of force just to produce a minimal deflection. In that split second, Roth was painfully aware that he was about to become yet another tragedy born of the brutal evolution in aerial combat technology. A casualty of a revolutionary device few in Germany's engineering community had fully comprehended. In the seconds that followed, the inevitable happened. 20-millimeter shells tore through his canopy, shattering it apart and exposing him to the bitter air of the German sky. As his FW-190 spiraled downward, tumbling toward the earth and the countryside below, Roth instinctively understood that he was no longer fighting just an enemy plane. Instead, he was battling the insidious effects of a technological breakthrough, an unanticipated innovation that had caught the German Luftwaffe's finest minds entirely off guard. This was the spring tab, a seemingly simple mechanical device, integrated into the Hawker Tempest's aileron system, yet so powerful that it redefined what was possible in high-speed aerial combat. The spring tab system transformed the Tempest's control capabilities, making it capable of maneuvering at speeds where traditional aircraft would have become uncontrollable. This effect was so profound that it destroyed the aerodynamic assumptions that German pilots had relied upon for years. By February of 1945, this innovation had already begun to take a tragic toll. 47 Luftwaffe pilots lost their lives in January alone during engagements where the Tempest's advanced control system rendered their own aircraft nearly impossible to handle at speeds exceeding 350 miles per hour. Many of these pilots discovered too late that their aircraft, even the most advanced and meticulously engineered fighters like the Messerschmitt Bf-109 and Focke-Wulf FW-190, became unmanageable in the face of this technological disparity. This disparity, where the British fighters maintained perfect maneuverability at speeds that Germany's aircraft could scarcely control, turned what was once a contest of skill and bravery into a brutal execution. The tragic story of Germany's vulnerability in high-speed control systems began months earlier, during the summer of 1944, when reports first surfaced at the Luftwaffe's command headquarters. These early reports described a new British fighter aircraft that seemed to challenge the very laws of aerodynamics, an aircraft that could maintain full aileron control at velocities where the traditional fighters, like the Messerschmitt B, F-109, and the Focke-Wulf FW-190, experienced control forces so severe that pilots could scarcely move their control sticks enough to maneuver effectively. Major Wilhelm Steinmann, who commanded two groups of Jagdgeschwader 26, dismissed these initial reports as either exaggerated or false. He insisted that no aircraft could sustain such precise and responsive control at 400 miles per hour, because the immense aerodynamic pressure at such velocities would physically prevent large control surface deflections unless hydraulic assistance was implemented. But adding hydraulic systems would have increased the weight and mechanical complexity of the fighters, a trade-off that no single-engine German fighter of the time could afford or justify. Major Steinmann's skepticism stemmed from his deep familiarity with the capabilities and limitations of the Luftwaffe's finest fighters. Having flown and commanded many missions with the FW-190, he understood that even this highly advanced aircraft required enormous physical effort from its pilots to maneuver at high speeds. Usually, a pilot needed to exert between 45 and 60 pounds of lateral force on the control stick to perform even modest rolls above 150 miles per hour. The control forces, therefore, were a significant limiting factor, often preventing pilots from executing the rapid, precise maneuvers needed in combat at such velocities. The situation was even significant physical effort in any other aircraft of the era, giving the Tempest a decisive edge in combat scenarios where quick, precise maneuvering was crucial. This innovative control system effectively shattered the previously accepted notion that high-speed fighters must inevitably compromise their maneuverability due to insurmountable aerodynamic and physical constraints. Before the introduction of this technology, pilots of the German Luftwaffe faced an alarming dilemma. As their aircraft accelerated toward combat speeds, their ability to control the aircraft diminished markedly. The cockpit design, with its limited space and narrow confines, physically prevented pilots from exerting more than roughly 45 pounds of lateral force on the control stick. Such a restriction rendered full aileron deflection, an essential maneuver for high-speed turns, impossible when flying at maximum velocities. The result was a tragic and persistent weakness that led to the loss of hundreds of German pilots, who found themselves unable to respond effectively during dives or evasive maneuvers against the more agile Allied fighters. As the aircraft's speed increased, the pilots encountered progressively heavier controls, which felt as though they had been cut from solid stone rather than crafted from metal and composites. This formidable obstacle appeared to stem from the fundamental laws of physics, specifically aerodynamics. As the speed of an aircraft grows, the aerodynamic forces acting on control surfaces intensify exponentially, demanding ever more strength from the pilot to overcome them. This created a perilous paradox. The faster the aircraft flew, the less maneuverable it became, transforming high-velocity fighters into essentially straight-line missiles that could hardly roll or turn. Catastrophic limitations in a dynamic aerial combat environment. Recognizing these issues, German aerospace engineers experimented with various methods to alleviate control forces at high speeds. One such solution involved fitting Flettner tabs onto some versions of the Bf-109G. These small auxiliary surfaces, known as Flettner or servo tabs, were designed to reduce the physical effort required to move the ailerons. Though they provided some marginal improvement, their implementation was limited. Only a handful of aircraft received these modifications, leaving the vast majority of Luftwaffe pilots to rely on raw physical strength and meticulous speed management to maintain control during high-speed dogfights. Within the German aviation community, the consensus was that reducing control forces at elevated speeds without resorting to hydraulic assistance was an insurmountable technical challenge. Engineers working across facilities in Augsburg, Dessau, and Recklinghausen had essentially accepted that heavy controls were an inevitable trait of high-performance fighters. They believed this limitation was universal, affecting all nations engaged in aerial combat at the time. They considered the physics of aerodynamics as an insurmountable barrier, one that could not be overcome with existing technology. This deeply ingrained belief proved devastatingly incorrect when operational experience with the British Hawker Tempest began to demonstrate otherwise. In April of 1944, the Tempest entered combat, bringing with it a groundbreaking control technology that the Germans had not even considered: spring-tab ailerons. These spring-tab mechanisms automatically modulated control forces, making high-speed maneuvering more manageable without the need for hydraulic boosters or other complex systems. The design of the spring-tab system was surprisingly straightforward. Each aileron was equipped with a small auxiliary control surface, called a spring tab, mounted on its trailing edge. This tab was linked to the main control system via a calibrated spring that would compress under aerodynamic loads. As the aircraft's speed increased, the aerodynamic forces acting on the control surfaces grew heavier, causing the spring to compress further. This compression moved the spring tab in the opposite direction of the pilot's control input, generating an aerodynamic force that assisted the main aileron movement. Essentially, the spring tab acted as a passive, automatic force multiplier. The faster the aircraft went, the more help the tab provided. This mechanism meant that as the aircraft's speed climbed and control forces would normally become unmanageable, the spring tab system automatically compensated, maintaining a relatively constant, manageable pressure on the control stick. When the Tempest was tested, British test pilot Eric Brown, later famed for evaluating captured enemy aircraft, remarked that the aircraft's controls felt almost unnaturally responsive at high speeds. The ailerons responded with a smoothness and sensitivity that allowed pilots to perform rapid, precise maneuvers, seemingly with minimal effort. This technological innovation granted the Tempest a tactical advantage, allowing it to maintain high roll rates and rapid directional changes, even at speeds where most other fighters would struggle to respond. The aircraft's ease of control at high velocities defied the previously accepted limitations imposed by physics and cockpit design. It demonstrated conclusively that the perceived inevitability of heavy controls at speed was, in fact, a problem that could be overcome through clever mechanical design. The significance of the spring tab system extended beyond mere pilot comfort. It fundamentally changed the way high-speed fighters could be operated, offering a new level of agility and responsiveness in the heat of combat. The Germans, who believed that control heaviness was an intrinsic and insurmountable feature of high-performance aircraft. During the intense aerial battles of late 1944, a remarkable phenomenon began to emerge that challenged the very foundations of aerial combat doctrine as understood by the German Luftwaffe. Pilots operating the formidable Messerschmitt fighters reported experiencing an almost superhuman level of control, a sensation akin to steering a vehicle with power steering long before that technology became commonplace. This sensation was characterized by a level of responsiveness and ease that allowed pilots to execute highly precise, effortless input commands, even at velocities where most aircraft of the era would become difficult to control, or in some cases, completely unmanageable. This extraordinary capability was not accidental, but the result of meticulous and deliberate development, involving extensive wind tunnel testing conducted at the Royal Aircraft Establishment in Farnborough. Engineers from Hawker Siddeley, working alongside their counterparts at the Langley facility, dedicated months to refining the aircraft's control surface mechanisms. They focused specifically on optimizing the spring rates and tab geometry, small mechanical adjustments that dramatically affected how the control surfaces responded. The goal was to reduce the force needed to achieve desired control inputs without risking flutter or aeroelastic problems, dangerous vibrations that could ultimately cause structural failure during high-speed flight. The realization of this advanced control system first made its presence known to German pilots during the Normandy campaign in 1944. As the British Tempests began appearing in increasing numbers over the battlefield, early combat reports started describing a series of seemingly impossible maneuvers. German pilots observed their adversaries executing aggressive rolls, tight turns, and rapid climbs at speeds that made their own fighters nearly inert, operating at the edge of aerodynamic and control authority, yet remaining controllable. The Tempest pilots seemed to possess an almost supernatural ability to maneuver at high velocities, leaving their German counterparts bewildered and increasingly frustrated. One particularly illustrative encounter occurred in September of that year over Belgium, when Joseph Priller, a highly experienced ace of the Luftwaffe with over 100 confirmed victories, engaged a Tempest during a high-speed dogfight. Priller later recounted how his Focke-Wulf 190 felt like flying through concrete once the aircraft exceeded around 400 miles per hour, a speed at which German fighters typically maintain some control, but not with the agility that the Tempest displayed. In stark contrast, the British fighter danced effortlessly around him, executing complex maneuvers such as barrel rolls that, in his experience, would have been physically impossible to perform at such speeds. These combat reports, accumulating throughout the autumn months, painted a disturbing picture. A technological gap was emerging that cast doubt on the perceived superiority of German aircraft. German pilots consistently described feeling outmaneuvered at high speeds, often unable to maintain straight flight paths as their aircraft became virtually unresponsive, while Tempests maintained their agility and control. The gravity of this issue was especially pronounced for pilots flying the Bf-109, whose narrow cockpits limited their ability to apply lateral stick forces effectively. This physical constraint meant that during high-speed dives, maneuvers often used to escape or gain positional advantage, they could find themselves trapped in nearly straight-line trajectories, unable to respond to the Tempest's superior agility. Meanwhile, British pilots took advantage of their aircraft's control system, following their German counterparts at high speed with ease, maintaining full maneuverability throughout the descent. By November of 1944, the situation had become urgent enough to prompt a top-level response. General Durjagdflieger Adolf Galland, a legendary fighter pilot and commanding officer, ordered an in-depth investigation into the extraordinary capabilities of the Tempest. A team of engineers from the companies Meshmet and Focke-Wulf was tasked with analyzing combat footage and examined wreckage from crashed aircraft. Their objective was to uncover the secret behind the Tempest's seemingly supernatural control at extreme speeds, an enigma that was rapidly becoming a major threat to German aerial tactics. Initially, the engineers' efforts focused on incorrect assumptions, as they believed that the British had developed some form of advanced hydraulic booster system or revolutionary aerodynamic design. They failed to recognize that the key to the Tempest's exceptional high-speed maneuverability lay not in complex or exotic systems, but rather in a simple yet ingeniously designed mechanical device. This device, which was visible in the wreckage of crashed aircraft but dismissed as nothing more than a trim tab, an ordinary component used for fine-tuning aircraft stability, was in fact the critical element. The breakthrough finally arrived in December of 1944, when Luftwaffe technical intelligence officers, based at Reclan, uncovered a significant piece of the puzzle. Their examination of a relatively intact aircraft revealed the presence of a particular system that fundamentally altered control forces at high speeds. This discovery explained how the British Tempest pilots could wield such extraordinary control over their aircraft, effectively turning what was once considered a limitation, control force requirements, into an advantage through meticulous mechanical refinement. This insight not only challenged existing assumptions, but also underscored the importance of seemingly simple mechanical solutions in advanced aeronautical engineering, highlighting how small adjustments could dramatically influence aircraft performance in combat situations. During a recent incident involving a tempestuous crash near Rain Airfield, investigators uncovered startling insights into aircraft control systems that could have far-reaching implications for aerial combat. This particular crash, which initially appeared to be a tragic accident, turned out to be a pivotal point in understanding the true nature of an innovative mechanism known as the spring tab system. This discovery revealed for the first time the profound impact that this seemingly simple mechanical device could have on improving aircraft maneuverability, especially at high speeds. As investigators examined the wreckage and reviewed the performance characteristics of the aircraft, they gradually realized that this straightforward control surface system had the potential to resolve a long-standing problem that had been plaguing German pilots for many months. The engineers, led by the meticulous and highly respected Dr. Friedrich Zimmermann from the Deutsche Versuchsanstalt für Luftfahrt, initially refused to accept the significance of their findings. They were skeptical that a device as uncomplicated as the spring tab could produce such dramatic improvements in aircraft handling. In a hurried series of calculations, Zimmermann's team confirmed that the spring tab system could reduce control forces by up to 70% at the aircraft's maximum speeds, effectively making difficult maneuvers much easier for pilots. This revelation was startling, as it challenged prevailing assumptions about aircraft control and hinted at a revolutionary technological advantage that had previously gone unnoticed. Zimmermann's detailed report, which he submitted to the Air Ministry, described the discovery in stark, unambiguous terms. The document pointed out that the enemy had equipped their latest fighter aircraft with a control system that offered unprecedented benefits, benefits that had not been anticipated in strategic planning. This system enabled their pilots to maintain full maneuverability during combat, even at speeds where the Germans' own aircraft became nearly uncontrollable. The report emphasized that integrating such a control mechanism into German fighters would not be a simple matter. It would require extensive redesigns of the aircraft's structure, coupled with rigorous flight testing. These modifications could take months or even years to implement effectively, adding urgency and complexity to the ongoing development efforts. The gravity of this discovery soon prompted a crisis meeting at the headquarters of the Luftwaffe's research division. During this gathering, the legendary fighter pilot and tactical leader Adolf Galland confronted Hermann Göring directly, laying bare the uncomfortable reality. British fighters had gained a decisive technological edge that could not be quickly neutralized. This revelation deepened the rift within the Luftwaffe's leadership, exposing the growing disparity between Allied technological advances and German development capabilities. The tension was palpable, with strategic concerns mounting about how to respond to this new challenge in the ongoing air war. Meanwhile, the Axis powers, including Japan and Italy, faced their own shock when encountering American fighters equipped with cutting-edge control systems. Japanese pilots of the Imperial Japanese Army Air Force, in particular, discovered that their fighters, primarily the Zero and other operational models, became virtually unflinching at high speeds. This was especially evident when engaging against American fighters like the P-51 Mustangs and P-47 Thunderbolts, which continued to respond crisply and accurately even as velocities neared or exceeded 300 miles per hour. The Japanese pilots, however, never fully grasped the specific technical innovations behind this disparity. They simply knew that the American fighters felt distinctly more agile and manageable, even under intense high-speed maneuvers. Prominent among the Japanese fighters' aces was Makoto Ogawa, who famously shot down 7 B-29 bombers during the latter stages of the war. Ogawa, in his post-war memoirs, vividly described the difficulty of engaging American fighters in high-speed dogfights. He likened it to fighting with one hand tied behind his back, explaining that as the fighters accelerated beyond 300 miles per hour, control forces became so heavy that aggressive maneuvers, such as tight turns and sudden climbs, became physically impossible. This control heaviness severely limited the Japanese pilots' ability to execute their usual tactics and left them at a significant disadvantage. The Italians, too, experienced similar control issues with their fighters, notably the Macchi C-202 Filori and C-205 Veltro models. These aircraft incorporated various attempts at mitigating high-speed control heaviness, such as interconnected aileron flap systems designed to aid pilot effort. Despite these modifications, their effectiveness paled in comparison to the British spring tab system. The Italians, along with their German allies, found themselves vulnerable to the same high-speed control limitations that hindered their performance in combat. Italian squadron leader Franco Lucini, one of the country's most renowned aces, repeatedly voiced frustration over these issues, describing the Macchi fighters as feeling wooden during high-speed pursuits. He recounted that even basic maneuvers, like sharp turns or evasive actions, required extraordinary physical strength and effort from the pilots when flying at speeds above 300 miles per hour. The development of the spring-tab-controlled aircraft, particularly the Tempests, began at the Hawker Aircraft's Langley facility in the year of 1943. Following rigorous and extensive flight testing, engineers and pilots alike refined the design of the control surface system to its optimal form, carefully calibrating spring rates and tab dimensions to ensure maximum responsiveness and maneuverability. This meticulous process aimed to enhance aircraft agility without risking structural damage, striking a delicate balance between performance and safety. The first batch of production, comprising 100 units of the Tempest Series 1, was equipped with this innovative spring tab control mechanism, which quickly proved its worth in combat scenarios. However, late in the year 1944, some of these aircraft were temporarily removed from active service after it was discovered that their significantly improved maneuverability could, under certain circumstances, impose excessive stress on the airframe. Specifically, pilots pushing their aircraft to the limits during high-speed maneuvers could induce structural fatigue, necessitating minor reinforcements to the airframe and additional pilot training aimed at understanding the nuances of the aircraft's new handling characteristics. Sidney Cam, who served as Hawker's chief designer, recognized early on during the Tempest development that controlling high-speed flight would pose a substantial challenge. Drawing upon his previous experience with the Typhoon, a fighter aircraft plagued by controls so heavy that pilots fatigued quickly during prolonged engagements, Cam understood that improving control response was vital for operational effectiveness. This insight was further supported by collaborative efforts with the Royal Aircraft Establishment, where aerodynamicists dedicated their research to finding reliable methods of reducing control forces at high speeds. Over time, they identified the spring tab system as an ideal solution because it offered a powerful combination of effectiveness, simplicity, and dependable performance, all while avoiding the added weight, complexity, and maintenance demands characteristic of hydraulic control systems. The manufacturing process for spring tab-equipped ailerons demanded a remarkably high degree of precision. Each aircraft's spring mechanism had to be calibrated meticulously, with individual testing to ensure that the control surfaces responded appropriately at all speeds. This level of quality control was particularly notable given the increasingly difficult conditions faced by German manufacturers in 1944, as Allied bombing campaigns severely degraded factory capabilities across the Reich. At Hawker's Langley plant, many of the assembly tasks, especially the delicate installation of the spring tabs, were undertaken by women workers who had taken over responsibilities after the enlistment of many men into military service. These workers measured tolerances in the thousandths of an inch, fully aware that their painstaking precision work could mean the difference between life and death for a pilot engaged in combat at speeds exceeding 400 miles per hour. The effectiveness of the spring tab system in combat was vividly demonstrated between December 1944 and February 1945. During this period, squadrons equipped with the Tempest 5 scored a remarkable total of 239 enemy aircraft destroyed, suffering only 20 Tempests in return. This translated into an impressive 7-to-1 kill ratio, a statistic not merely reflecting pilot skill, but underscoring the decisive advantage conferred by the aircraft's superior control at high speeds. In particular, squadron leader David Fairbanks, who became the highest-scoring Tempest ace, recounted numerous encounters with German fighters attempting to escape reconnaissance or attack engagements by diving away at high speed. However, these efforts often failed because the Tempest's enhanced control system allowed Fairbanks and his pilots to perform aggressive maneuvers, maintaining optimal firing positions and turning what could have been successful retreats into easy targets. His exploits exemplified how the system transformed high-speed escapes into virtual turkey shoots, where the enemy fighters found themselves trapped in straight-line dives, unable to evade the relentless pursuit. The psychological impact on Luftwaffe pilots was profound and often devastating. Once they realized that their aircraft suffered from a fundamental disadvantage, namely, the inability to maintain control during high-speed maneuvers, the confidence in their aircraft's agility eroded rapidly. This sense of vulnerability created a crisis of confidence that spread through German fighter units that regularly faced the Tempest in combat. Pilots who once relied on their aircraft's agility now found themselves at a severe disadvantage, both tactically and psychologically, as they struggled to understand whether tried-and-true tactics no longer worked against the more responsive Tempest. The inevitable result was a growing sense of frustration and helplessness among German pilots, which further tilted the balance of aerial combat in favor of the Royal Air Force's most formidable fighter aircraft during those critical late-war months. Bulligan of Jagasheer, a seasoned veteran who had flown over 100 combat missions during the tumultuous days of the Second World War, vividly described the relentless technological gap faced by German pilots in his letter to his wife, penned in January of 1445. He remarked that their forces were fighting with outdated weapons, symbols of a bygone era, against the rapidly evolving and far more sophisticated machinery of tomorrow. His words evoked a sense of helplessness, a feeling of watching helplessly as enemy tempests, with their advanced maneuverability and incredible speeds, danced effortlessly through the skies, outpacing the capabilities of his beloved Focke-Wulf 190, which now felt sluggish and cumbersome, even as laden with fuel or armament as a fully loaded bomber. The attempts by German engineers and aviators to swiftly develop and deploy comparable control systems faced formidable obstacles that seemed insurmountable in the face of wartime adversity. The German aviation industry, already strained under the weight of material shortages, was hampered by the widespread dispersal of aircraft factories, an obstacle caused by relentless Allied bombing campaigns, and the significant loss of experienced engineers who had either been conscripted into military service or captured by Allied forces. These setbacks made it nearly impossible to undertake the extensive redesign, testing, and implementation processes necessary for integrating innovative control mechanisms, such as the spring tab system, into existing aircraft. The difficulties became so profound that, by the end of the war, only a few aircraft models, notably some variants of the FW190D13, were equipped with rudimentary hydraulic aileron boost systems, introduced as an emergency measure to provide minimal relief in control difficulties. However, only a small number of these aircraft ever left the assembly lines before defeat was finalized, and the added weight and mechanical complexity of this rudimentary system ultimately compromised aircraft performance in various flight regimes, rendering it a poor substitute for the elegant and functional simplicity of the original spring tab concept. The Luftwaffe's fighter force, already beleaguered by a host of pressing issues, fuel shortages, the scarcity of well-trained pilots, and an overwhelming numerical disadvantage, found itself further hampered by the technological limitations of its aircraft's control systems. This technological gap became a critical factor, tipping the scales against them, accelerating their decline in the skies. As a consequence, many pilots consciously avoided engaging in high-speed dogfights, knowing that such encounters would place them at a severe and often fatal disadvantage against aircraft like the Tempest, which could execute maneuvers with far greater ease and precision. Instead, missions such as the infamous Boden-Platte raid on January 1st, 1445, reflected a strategic shift. The Luftwaffe launched large-scale surprise attacks on Allied airfields, driven by the urgent need to destroy enemy fighters on the ground, an acknowledgement that aerial combat at high speeds had become an act of almost suicidal risk for their pilots. Facing Tempests with their superior control and handling characteristics, German pilots found themselves increasingly unable to match the agility and resilience of the enemy fighters in the air, leading to mounting casualties and a sense of helplessness in the cockpit. The influence of the spring tab control system extended well beyond mere combat effectiveness. Tempest pilots benefiting from these advanced control surfaces could adopt aggressive pursuit tactics that would have been physically exhausting and unsustainable when flying traditional fighters. The spring tab mechanism significantly reduced the physical effort required to execute precise control inputs, allowing pilots to sustain longer missions with less fatigue, thus maintaining peak operational performance over extended periods of combat. This advantage was noted repeatedly by pilots who transitioned from older aircraft to the Tempest, discovering firsthand how the improved control system made their flying experience markedly less strenuous, yet more effective. One such pilot, Flight Lieutenant Pierre Klustermann, serving with the renowned 274 Squadron, documented that after switching from the Spitfire to the Tempest, he found himself able to fly for twice as long without experiencing the debilitating arm and shoulder fatigue that had previously limited his endurance and precision during prolonged dogfights. The subtle but impactful design of the spring tab controls made maneuvering feel as natural as moving through the air itself, rather than fighting against the aircraft's resistance, at speeds typical of high-speed combat. Such improvements in control comfort translated directly into combat advantages, allowing pilots to maintain aggressive tactics without succumbing to physical exhaustion as quickly as they would have with conventional control surfaces. After the war, extensive technical analyses were carried out at a designated testing facility in the United States, where captured German fighters were subjected to rigorous examination. American test pilots, with their extensive experience, confirmed the severe control force issues that had plagued the German fighters, particularly the FW190 series. They expressed astonishment that German pilots had managed to achieve any success at all, given the severe physical limitations imposed by the aircraft's high-speed control forces. These evaluations revealed that, despite the FW-190's reputation for excellent handling at low and medium speeds, the aircraft became exceedingly difficult to control above approximately 400 miles per hour, an indication that at such velocities, the challenges faced by fighter pilots during World War II were often more about the aircraft's design limitations than individual skill. For instance, the German Messerschmitt Bf 109G, a widely used fighter, was hampered by a notably narrow cockpit that made it physically difficult for pilots to exert enough lateral force on the control stick to achieve full aileron deflection. This restriction significantly impaired maneuverability, especially during high-speed combat when quick and precise control inputs are crucial. The situation was arguably even worse with the Focke-Wulf FW-190, another formidable German fighter. Unlike some of its counterparts, the FW-190 lacked spring tabs or similar control aids, features designed to reduce pilot workload by easing the force needed for control surface movements. As a result, at maximum speeds, pilots found it nearly impossible to manipulate the ailerons effectively, rendering them practically useless in critical moments. To put it plainly, the aircraft's flight controls could, under extreme conditions, become so stiff as to be nearly non-responsive, severely limiting combat performance. In contrast, British aircraft like the Hawker Tempest offered a different experience. Test pilots and military observers noted that the Tempest maintained a consistent and responsive feel across its entire speed range. The aircraft's controls remained sensitive and manageable, even at high velocities, providing pilots with the confidence and precision necessary for effective combat maneuvers. An experienced pilot once vividly described the difference as comparable to the difference between wielding a weapon and wielding a club, highlighting the stark contrast in control responsiveness. While the Tempest controls allowed for smooth handling, the German fighter's lack of advanced control aids like spring tabs resulted in a significant disparity, especially under demanding conditions. This disparity was so significant that observers, including Captain Eric Brown of the Royal Navy, who conducted extensive tests on both German and British fighters, concluded that the combination of a narrow cockpit and heavy, stiff controls in aircraft like the Bf 109G created what could only be described as a death trap during high-speed dogfights. Pilots, regardless of their skill or levels of determination, simply could not generate enough physical force to maneuver effectively at critical moments. This fundamental flaw limited the combat effectiveness of some German fighters and placed their pilots at a severe disadvantage. The Italian evaluation of captured Allied aircraft after Italy's surrender in the war revealed a similar sense of amazement at the advanced control systems found in British fighters. Regia Aeronautica test pilots reported that flying a Tempest after their experiences with the Macchi fighters, Italian versions of the earlier Hawker Hurricane, was akin to switching from driving a heavy truck to racing a sports car. They particularly noted how easily they could control the aircraft at speeds where their own fighters demanded maximum physical effort from the pilot. One prominent Italian fighter ace, Major Adriano Visconti, who was among Italy's most successful pilots during the conflict, tested a captured Tempest in early 1945. He observed that if Italian fighters had been equipped with similar spring tab systems, control aids designed to lighten the pilot's workload, it could have revolutionized Italian air combat tactics over the Mediterranean theater. Visconti remarked that such a technological upgrade might have significantly shifted the balance of power in aerial battles, making high-speed maneuvers more feasible and safer for Italian pilots. Despite their reputation for innovative aircraft design, the Japanese never fully addressed these high-speed control problems. Their emphasis on lightweight construction and exceptional maneuverability at lower speeds meant that their fighters lacked effective solutions for maintaining control effectiveness at high velocities. Consequently, Japanese fighters often found themselves essentially helpless in high-speed engagements against American aircraft, which were increasingly equipped with advanced control systems that preserved agility and responsiveness even at extreme speeds. Post-war interrogations of Japanese pilots confirmed that many did not understand why American fighters could outmaneuver them at high speeds. They often attributed their losses to superior pilot training or mysterious, unidentified technology. However, they largely failed to recognize the pivotal role played by control systems such as spring tabs, small but vital devices that electronically and mechanically aided pilots by reducing the physical effort required to move control surfaces across the entire speed range. This oversight meant they underestimated one of the key technological advantages that gave Allied fighters their edge in high-speed combat. Following the war, Soviet engineers and designers studied the captured German aircraft extensively, alongside limited British technical documents received through Lend-Lease arrangements. They quickly recognized the vital importance of reducing the physical force necessary to operate control surfaces, which could significantly improve aircraft responsiveness and pilot endurance. Although initially struggling to replicate the elegant simplicity of the British spring tab system, Soviet engineers prioritized the development of similar solutions in their post-war fighter designs. The Yakovlev Design Bureau, in particular, dedicated considerable effort to solving this problem. Alexander Yakovlev himself pointed out that the spring tab represented a straightforward yet highly effective solution to a complex challenge that had previously been approached incorrectly. This realization led to significant improvements in Soviet control systems, and later Soviet fighters benefited from more sophisticated and responsive controls, partly thanks to the insights gained. Following the conclusion of hostilities, the French aviation sector embarked on an ambitious effort to reconstruct and modernize its aircraft industry, which had been severely damaged during the war. This revival was facilitated by access to advanced technological insights, not only from German engineers, but also from Allied sources, allowing for a comprehensive research phase focused on improving aircraft control systems. During this period, engineers working under the auspices of the SNKCMA, an influential aircraft development center, carried out extensive studies into different control mechanisms, aiming to enhance aircraft maneuverability and pilot safety. Their investigations led to a remarkable realization: the integration of spring tab mechanisms into control surfaces, particularly ailerons, represented one of the most significant yet often underappreciated technological breakthroughs of the war. These innovations granted aircraft an unprecedented level of agility and responsiveness, providing tactical advantages that, in numerous instances, decided critical aerial battles, even though many of the pilots and commanders remained unaware of the precise technical reasons behind their aircraft's superiority. One of the key advocates for the widespread adoption of such innovations was Marcel Dassault, an influential engineer and visionary whose company would later evolve into one of Europe's foremost manufacturers of fighter aircraft. Observing the bleak aftermath of the war, Dassault was deeply convinced that future fighter designs must incorporate advanced control assistive devices, features that could dramatically enhance pilot responsiveness in aircraft handling. He had witnessed firsthand the devastating consequences of control force limitations that had hampered Axis fighters, often restricting their agility just when maximum maneuverability was most needed. Such limitations frequently resulted in critical losses during dogfights, with pilots unable to respond swiftly to changing combat scenarios. Motivated by these experiences, Dassault championed the integration of spring tab control systems into aircraft designs, emphasizing their potential to improve combat effectiveness substantially. The tangible results of these technological advancements are reflected vividly in the production statistics during the war's final years. For instance, the British aircraft manufacturer Hawker, under wartime pressures, produced approximately 1,720,000 Tempest fighters by the conclusion of the conflict. A significant proportion of these aircraft, most of which were equipped with advanced spring tab ailerons, were instrumental in maintaining Allied air superiority. Meanwhile, efforts by the German aviation industry to retrofit similar control systems onto their existing fighters proved to be far less successful. Only a handful of aircraft received such modifications before the collapse of the Reich's military capabilities. By early 1945, the Langley factory in Britain was exporting Tempest fighters at a staggering rate of roughly 15 aircraft per week, each representing another formidable asset capable of dominating high-speed aerial combat zones. This rapid manufacturing pace starkly contrasted with the struggles faced by German factories, which found it increasingly difficult to sustain operational levels amidst relentless Allied bombing campaigns and chronic shortages of vital resources. As a result, the German Luftwaffe suffered devastating losses, particularly among experienced pilots, due to the inability to replace personnel properly or maintain effective training programs. The human toll was staggering. In the month of January alone, when 47 German pilots lost their lives fighting Tempests, the Luftwaffe experienced the equivalent of an entire fighter group's worth of seasoned pilots wiped out in a single month. This loss was compounded by the poor quality of replacements, many of whom had minimal flight hours and insufficient training, making them ill-prepared for the rigors of combat against well-trained Allied pilots flying aircraft equipped with advanced control systems. Beyond the immediate tactical and strategic advantages, the psychological impact of the spring tab innovation on German pilots and commanders must not be underestimated. Rumors and reports of the Tempest's extraordinary maneuverability soon spread through Luftwaffe units, creating an aura of almost supernatural capability around the aircraft. This aura bred fear and defeatism among German pilots, undermining their confidence even before they engaged in combat. Pilots who had once displayed aggressive tactics and unwavering confidence found themselves hesitating and adopting more defensive postures, fully aware that confronting a Tempest at high speeds was virtually a suicide mission. The psychological burden of knowing they faced aircraft with seemingly near-supernatural agility led to a cascade of disadvantages. German fighters were forced to fight from positions of weakness, often attempting to avoid direct engagement altogether or engaging only in unfavorable circumstances. The significance of the spring tab system in shaping the outcome of aerial battles was later acknowledged by Wing Commander Roland B. Mont, who commanded the first Tempest wing into operational combat. He reflected that the mechanical simplicity of the spring tab control mechanism had provided an unexpected tactical advantage, a sort of ace-up-our-sleeve that the Germans had failed to anticipate. In Beaumont's view, this innovation transformed what might have been an ordinary fighter into a highly dominant aircraft, solely through the application of a relatively straightforward mechanical device. Many of his pilots, he noted, did not fully comprehend the extent of their aircraft's superiority, often attributing their success to exceptional training or tactical prowess. Yet the real edge lay in the aircraft's fundamentally enhanced control characteristics, which made high-speed maneuvers, and thus combat engagements, far more favorable for the Allies, ultimately helping to shift the balance of the advantages of the spring tab control system, particularly in terms of maintenance and reliability, proved to be quite significant when compared to hydraulic alternatives. Unlike hydraulic systems, which tended to be more complex, heavier, and susceptible to failures, the mechanical nature of the spring tab system meant that it required minimal upkeep and was rarely prone to malfunction. This simplicity not only reduced maintenance costs and downtime, but also ensured consistent performance, especially in the demanding environments of wartime operations. While hydraulic systems involved intricate plumbing, specialized hydraulic fluid, and the need for highly trained personnel to service them, ground crews at forward airfields could easily maintain and adjust the spring tab mechanisms using only basic tools. In contrast, hydraulic systems often demanded sophisticated equipment and expertise that, as the logistical situation deteriorated, particularly for the struggling Luftwaffe, became increasingly difficult to sustain and operate effectively. Furthermore, the aerodynamic efficiency of the spring tab design itself warrants significant recognition. These small control surfaces, or tabs, were deliberately designed to exert enough influence to improve aircraft handling without introducing substantial aerodynamic drag. Their minimal size meant they added very little resistance to airflow, thus ensuring the aircraft maintained high speeds and optimal performance. Larger control aids, such as balance tabs or other mechanical devices, could adversely affect the aircraft's aerodynamic profile, slowing it down and reducing maneuverability. an unacceptable compromise in the context of fighter aircraft where every mile per hour and every ounce of agility could spell the difference between life and death. The delicate balance achieved through this small control surface exemplifies a design philosophy that prioritized functionality with economy and precision. The refinement of the spring tab system was the result of extensive wind tunnel testing at Farnborough, where engineers meticulously optimized both the size and placement of these control surfaces. This rigorous experimentation aimed to maximize the reduction of control forces needed during maneuvering, all while minimizing the aerodynamic drag produced. The outcome was a highly refined solution, one that allowed pilots to achieve superior control with less effort and without sacrificing speed or agility. Such a level of engineering finesse was difficult for German designers who, under wartime pressure and with limited resources, could not afford the same meticulous approach. Their focus often leaned towards more complex and resource-intensive technologies that, while innovative, frequently proved less reliable and harder to produce on a large scale. The implications of the spring tab system extended well beyond mere combat performance. Its impact on training and pilot endurance was equally significant. Since the system reduced the physical effort required to control the aircraft, pilots could fly the Tempest more effectively with less strenuous physical conditioning. This was particularly advantageous for older pilots, or those with smaller stature, who might otherwise have struggled or been rendered ineffective when flying conventional fighters. By easing the physical demands of flying at high speeds and under combat stress, the spring tab system broadened the pool of capable pilots and contributed to lowering training failures, or washout rates. As the war prolonged and seasoned pilots became increasingly scarce, such technological benefits gained even greater strategic importance. While the Luftwaffe grappled with pilots who often lacked the physical strength necessary for effective control at combat speeds, the British invested in pragmatic engineering solutions like the spring tab. This approach embodied a fundamental contrast in design philosophy, embracing simple, reliable, and elegant mechanical solutions over complex, over-engineered systems that could be more prone to failure. British engineers opted for a straightforward combination of springs and small metal tabs, an approach that delivered superior performance without the complications of hydraulic or variable geometry systems. This pragmatic mindset reflected a broader difference in engineering culture, one that favored functionality and reliability, especially in wartime conditions where the ability to produce, maintain, and rely upon technology could greatly influence the outcome of battles. In stark contrast, German engineers often pursued highly sophisticated solutions, such as hydraulic control systems and variable geometry wings, seeking to push the boundaries of aeronautical technology. While innovative, these approaches frequently resulted in systems that were complex, difficult to manufacture in large quantities, and less reliable under the rigors of wartime service. The British, by focusing on simplicity and proven mechanical principles, achieved results that were not only effective, but also easier to produce and maintain in the field. This fundamental divergence between the pragmatic, streamlined British approach and the more intricate, ambitious German designs had far-reaching implications during the war, influencing aircraft performance, maintenance, and ultimately the technological edge of the Allies. Post-war analyses, including reports from the United States Strategic Bombing Survey, underscored the significance of technological advantages like the spring tab system. These innovations were seen to have far-reaching and cumulative effects that extended well beyond their immediate impact in combat. They contributed indirectly to the erosion of German morale. As aircraft became easier to control, pilots faced less physical strain, and maintenance constraints eased, all of which compounded into a broader decline in the Germans' technological edge. The report highlighted how the Germans had underestimated the importance of such incremental yet vital advancements, assuming a level of technological parity with the Allies that proved to be misguided. This failure to recognize the strategic value of smarter, simpler engineering solutions ultimately contributed to the deterioration of German capabilities, and the advent of the spring tab system represented a revolutionary breakthrough in aircraft control technology, fundamentally challenging the perceived superiority of German engineering at the time. Its introduction proved to be particularly disruptive to pilot confidence, exposing vulnerabilities that many believed were beyond the reach of conventional design principles. This innovation did not remain confined to the Second World War. Rather, its influence extended well into the post-war era, with various adaptations appearing in both civilian and military aircraft for many decades thereafter. The enduring presence of this technology and its variants underscore how a seemingly simple mechanical device, devised under the extreme pressures of wartime, could leave a lasting legacy on the development of aeronautical control systems. The core principle behind the spring tab, an ingenious yet straightforward solution, was initially envisioned and developed by the talented engineers at Hawker during the chaos of wartime. Their work laid the groundwork for what would become a fundamental concept in modern fly-by-wire systems. Contemporary aircraft equipped with fly-by-wire controls utilize artificial feedback mechanisms and automatically modulate control forces, all of which trace their conceptual origins back to those early, unassuming spring tabs. These mechanical devices provided pilots of the Tempest with a significant tactical edge, demonstrating vividly how innovation born amidst the rigors of war could influence aircraft design and control long after the conflict had ended. The story of the spring tab also serves as a stark reminder of the dangers inherent in overly relying on assumptions about technological limitations and the importance of relentless innovation. German engineers, convinced that high-speed flight control problems were insurmountable without deploying complex hydraulic systems, overlooked simpler and more effective solutions that their adversaries had already begun to implement. This misguided confidence created a critical blind spot, one that proved to be costly not only in terms of technical performance, but also in human lives. The failure to adopt spring tab technology contributed to the loss of hundreds of German pilots' lives, illustrating how a single overlooked innovation could tip the scales of strategic advantage and influence the outcome of aerial combat. In the final months of the war, this technological oversight significantly hampered Germany's attempts to challenge Allied air dominance. The inability to integrate the spring tab system into their aircraft meant that the Luftwaffe was often at a fatal disadvantage when facing well-controlled Allied fighters. Personal narratives from German pilots who had survived encounters with Tempests vividly depict the terror of helplessness at high speed, an experience made even more harrowing by the pilot's inability to maneuver effectively against an enemy fighter that maintained perfect control. These accounts reveal how what should have been an advantage, diving at high speed, became a death trap when pilots found themselves unable to respond to enemy maneuvers. One such account is that of Officer Wilhelm Hoffmann, a German pilot shot down by a Tempest in February of the year 1945. Hoffmann described his ordeal as akin to being paralyzed, a sensation of complete helplessness, while his aircraft, a Messerschmitt Bf 109G, lost all responsiveness at 400 miles per hour, even as the Tempest behind him moved with a grace that seemed almost dance-like. His words conveyed the visceral reality of combat stress and technological disadvantage compounded into a harrowing experience. Meanwhile, the industrial archaeology of the Hawker-Langley factory, though largely erased by post-war development, offers detailed evidence of the meticulous manufacturing processes involved in producing the spring tabs. The factory's equipment included specialized jigs and fixtures designed to produce consistent spring rates and precise tab alignment across hundreds of aircraft. Worker memoirs emphasize the rigorous quality control measures, with management stressing that accuracy as fine as a tenth of an inch could determine a pilot's survival. Such precision manufacturing underscored the recognition that these seemingly simple components were, in fact, vital safety and combat-enhancing technology, capable of tipping the balance in life and death situations. During the wartime, the spring tab technology was classified, and knowledge of its true purpose was deliberately kept vague even from some Allied pilots, who were often unaware of the extent of their aircraft's advantages. Squadron intelligence officers were instructed to describe the system in nebulous terms if captured, in order to conceal the secret weapon that contributed to their aircraft's superior control and maneuverability. The strategic importance of the spring tab remained hidden from many, even within the Allied ranks, until the full scope of its impact was understood long after the war ended. Despite their extensive efforts to gather technical intelligence on Allied aircraft, German intelligence services never fully appreciated the revolutionary significance of the spring tab system during the conflict. Their inability to decode or grasp the full benefits of this innovation exemplifies how technological secrets, when kept well, can dramatically influence the course of military engagements. The spring tab's subtle yet profound effect on aircraft control ultimately demonstrated that sometimes the most decisive advancements are not the most complex, but the simplest, most elegant solutions carefully concealed within the machinery of war. Until the tragic crash of the aircraft, the investigation into the control system malfunction was ongoing. But by that point, it was already too late to implement effective countermeasures or remedial actions. The discrepancies and shortcomings in control system design had far-reaching consequences, affecting not only the immediate tactical situation, but also imposing significant economic burdens. For instance, the conflict forced the Luftwaffe to divert valuable resources and manpower toward developing emergency solutions, such as hydraulic boost systems, that while helping in the short run, could have been better allocated elsewhere. These resources might have been more effectively spent on increasing aircraft production, improving pilot training programs, or advancing other technological areas to enhance overall combat readiness. The hidden costs associated with the pursuit of solutions to counteract the spring tab advantage highlight how technological inferiority can drain a nation's resources over time. Extensive man-hours were dedicated to investigating and devising workarounds for control system deficiencies, a process that represented a latent but substantial economic burden. Such efforts sapped Germany's wartime capacity, especially at a moment when every available resource was critically needed for the nation's survival and ultimate victory. The broader recognition of the significance of the spring tab system developed gradually, with many post-war accounts emphasizing more conspicuous innovations, such as jet engines or radar, while the importance of simpler mechanical devices like the spring tab was often overlooked. It was only with the benefit of hindsight, through detailed historical and technical analyses conducted in the following decades, that the true strategic importance of this modest yet influential innovation was recognized. In this evolving historical perspective, the accounts of ground crews stationed with the Luftwaffe reveal a different dimension of the control system crisis. Mechanics recounted stories of pilots returning from missions visibly exhausted, their muscles strained from fighting the overly heavy controls. Such physical fatigue sometimes incapacitated pilots, rendering them unable to fly again for days or even longer. This reality starkly contrasted with the experience of Tempest pilots who could undertake multiple missions within a single day without suffering comparable fatigue. Chief Mechanic Otto Bergmann from Jägerschwader Squadron 26 observed an increasing number of pilots requesting modifications, any adjustments that might lighten control forces. Desperate measures were taken on the field, including dangerous modifications such as removing armor plating to reduce weight, illustrating the severity of the disadvantages faced and their impact on pilot safety and aircraft integrity. The narrative of the spring tab system also underscores the vital importance of incremental innovation and persistent improvement in military technology. The control system fitted to the Tempest aircraft was not the result of a sudden breakthrough, but rather of a process spanning many years, rooted in interwar research and development efforts. These earlier efforts laid the groundwork for understanding how seemingly mundane technological advancements could yield decisive battlefield advantages. In particular, the evolution of control systems demonstrated how gradual refinements, driven by careful engineering and persistent experimentation, could produce significant operational benefits in wartime conditions. This story exemplifies the value of sustained investment in basic technological research, which often appears trivial during peacetime, but proves crucial in moments of crisis. The contrast between different national approaches to solving the control force challenge highlights the importance of methodology and technological development. The Royal Aircraft Establishment in Britain employed a systematic, rigorous approach, conducting extensive wind tunnel testing and theoretical analyses to understand control dynamics. This disciplined effort stood in stark contrast to the more ad hoc German approach, which often relied on intuition and incremental adjustments, but failed to identify effective solutions until it was too late. The cultural and organizational factors that influenced German engineers' failure to recognize the potential of spring tab technology merit careful consideration. A tendency within the German engineering community to favor complex, sophisticated solutions, often perceived as more impressive, may have hindered the adoption of simpler, more practical fixes that could have delivered immediate benefits. Furthermore, the focus of German innovation on revolutionary advances, such as jet propulsion and rocket technology, while undeniably impressive, might have inadvertently caused them to overlook the practical evolutionary improvements like spring tabs. These minor yet powerful adjustments could have provided immediate, tangible operational advantages in control and handling, but the emphasis on headline-grabbing breakthroughs overshadowed the pursuit of incremental, practical innovations. This tendency reflects a broader pattern in technological development, where ambitious, revolutionary ideas garner more attention and funding than steady, practical enhancements that can deliver immediate results. In conclusion, the story of the spring tab control system embodies the complex relationship between technological innovation, organizational culture, and strategic advantage. It demonstrates how patience, systematic research, and a willingness to pursue simple, practical solutions can ultimately yield decisive benefits in warfare. Conversely, it also illustrates the perils of overemphasizing dramatic breakthroughs at the expense of gradual improvements, and how organizational mindset and cultural values can influence a nation's technological trajectory, sometimes to its detriment. Recognizing the full significance of such incremental innovations emphasizes their often underappreciated role in shaping the outcome of military conflicts. The post-war expansion and adaptation of spring tab technology across various aircraft types exemplified its remarkable versatility and inherent robustness. This innovative control system, originally conceived by Hawker for the Tempest, found applications not only in military fighter aircraft, but also in a broad spectrum of civilian and transport aircraft, demonstrating that its fundamental principles could transcend the original design purpose. For example, the Douglas DC-6 and other post-war commercial airliners incorporated spring tab mechanisms that were directly inspired by wartime fighter innovations, illustrating a clear transfer of military technology into peacetime aviation markets. Such integration underscored how breakthroughs developed under the extreme pressures of war could, when refined, benefit civilian aircraft design and operation. Despite the origins rooted in the intense aerial battles of the years 2044 and 45, the connection between wartime combat innovation and peacetime application was rarely explicitly acknowledged. During those final fighting months, German forces made increasingly desperate attempts to counter the Allied air dominance, with strategic orders instructing their pilots to avoid engaging unless they held clear advantages in numbers and altitude. These tactical restrictions, aimed at preserving aircraft and pilots, inadvertently reduced the effectiveness of many German units, including the Luftwaffe's attempts to challenge Allied superiority. Such measures exemplified the adaptive tactics born out of a recognition of the technological advantages held by aircraft equipped with innovations like the spring tab system. One of the most tragic elements of this period was the deployment of Ramjer units, specialized units trained to ram Allied bombers in suicidal attacks. Their formation was motivated by the near impossibility of conducting traditional interception missions when facing fighters like the Tempest, which could dominate aerial combat through superior control capabilities at high speeds. The human element adds a layer of profound tragedy. Many young German pilots, some with fewer than 50 flight hours, were thrust into combat against Tempests, armed with spring tab systems designed to maximize control and maneuverability. These young men, often with minimal training, faced overwhelming technological and tactical advantages in a war that demanded impossible choices and often resulted in devastating loss. The disparity in skill and technological edge left many of these inexperienced pilots vulnerable as they encountered aircraft that maintained full control authority even at extreme speeds, an ability that was physically impossible for them to counteract effectively. Efforts to prepare new pilots involve specialized training schools aimed at understanding and mitigating control issues. However, no amount of instruction could fully compensate for the fundamental physical limitations posed by high-speed maneuvering in aircraft equipped with spring tab systems. The physical laws of aerodynamics meant that pilots, regardless of their skill or training, could not match the aircraft's inherent control capabilities without the benefit of technological assistance. The survival and analysis of wartime documentation concerning the development and deployment of spring-tab technology provide invaluable insights into the processes of military innovation during periods of urgent necessity. These records reveal how British engineers systematically approach solving complex technical problems, balancing the need for rapid production with the demands of combat effectiveness. Through meticulous research and iterative testing, they refined spring-tab mechanisms to enhance aircraft control, thereby giving designs like the Tempest a decisive edge in aerial combat. Correspondence between Hawker's design teams and RAF operational units highlights an ongoing process of refinement, driven by frontline feedback. This iterative approach involved continuous adjustments based on combat experience, ensuring that the technology evolved in tandem with the operational realities faced by pilots. Compared to the German approach, where deteriorating communication channels and fractured command structures hindered development, British engineers maintained close links with test pilots and frontline crews, facilitating rapid innovation. The crucial role of test pilots such as Bill Humble and Philip Lucas cannot be overstated. These men willingly risked their lives exploring the outer limits of aircraft performance to determine the optimal spring rates and tab configurations. Their methodical flight testing generated critical data, leading to incremental improvements that eventually resulted in the final spring tab designs. These configurations provided the Tempest with exceptional maneuverability and control, significantly enhancing its combat effectiveness and survivability against enemy fighters. The detailed reports compiled by these pioneering pilots, preserved within military archives, document the systematic approach undertaken, testing dozens of different configurations before arriving at the innovative design that endowed the Tempest with such a distinct tactical advantage. Following the conclusion of the war, spring-tab technology experienced widespread international dissemination. Former military and civilian aircraft manufacturers across multiple nations adopted and adapted the system, recognizing its potential to improve aircraft handling and combat performance. This proliferation underscored the enduring influence of wartime innovation, demonstrating how a technological breakthrough initially developed under the most stressful conditions could over time become a standard feature in aircraft design worldwide, influencing generations of aircraft well into the post-war era. In the course of wartime cooperation, former enemies found ways to turn their conflict into collaboration, sharing crucial technical insights that underscored how military innovations could transcend national borders and ultimately contribute to the advancement of global aviation. For instance, during the conflict, German engineers had faced significant difficulties in fully grasping the intricacies of spring-tab technology. This challenge did not prevent them from later contributing to its refinement and adaptation for civil aviation purposes after the war concluded, illustrating a profound shift from hostility to joint progress. Such cooperation demonstrated vividly that, even amid former adversarial tensions, the shared goal of improving aircraft performance could foster collaboration that benefited humanity as a whole. The effectiveness of the spring-tab system, particularly in high-performance fighter aircraft like the Tempest, is substantiated through meticulous statistical analysis of combat records. These records reveal a clear and consistent pattern. Tempest maintained superior exchange ratios against their German counterparts, even when faced with numerical disadvantages. This advantage was especially evident in high-speed dogfights, where the control systems equipped with spring tabs offered unparalleled maneuverability and responsiveness. This data underscores the tangible battlefield benefits that spring tabs conferred, transforming theoretical advantage into demonstrable combat success. In the realm of air combat, the conventional expectation was that numerical superiority would invariably tip the scales in favor of the larger force. However, the technological advantages embodied by the spring tab system challenge this assumption, effectively rewriting the rules of engagement. A single Tempest, thanks to its advanced control surfaces, could engage multiple German fighters that struggled to maneuver effectively at the same high speeds. This capacity drastically shifted the tactical landscape, allowing a lone aircraft to hold its own or even gain the upper hand against seemingly overwhelming odds, based purely on technological edge rather than sheer numbers. The sophisticated metallurgical engineering required to produce reliable spring tabs, presented its own set of challenges and advantages. The springs, crucial components of this system, had to maintain their consistent properties across a wide temperature spectrum and endure millions of compression and extension cycles without failure. British industry, benefiting from advanced metallurgical techniques and manufacturing capabilities, was able to produce these spring components more reliably than their German counterparts, whose industrial infrastructure had been increasingly strained and damaged by wartime losses. The requirement for specialized steel alloys, which became harder for Germany to source as raw materials and industrial facilities diminished, added another layer to the technological gap, further securing the advantage for Allied aircraft. Beyond the hardware itself, the psychological and tactical influence of spring tab technology on pilots and doctrine was profound. Knowing that their aircraft possessed superior high-speed maneuverability and control, Tempest pilots gained a significant confidence boost, enabling them to adopt aggressive tactics and seize the initiative. Conversely, German fighters, lacking comparable control system robustness, were compelled to avoid certain tactical scenarios, particularly high-speed slashing attacks, thus ceding ground to the Allies. This psychological and strategic shift meant that the engagement landscape was effectively reshaped, with German pilots often forced into disadvantageous turning fights, where their numerical inferiority and fuel constraints frequently determined the outcome. The documentation and dissemination of spring tab technology through technical manuals and pilot training programs played a crucial role in ensuring its effective deployment. These manuals contain detailed explanations, diagrams, and simplified principles designed to make the complex engineering concepts accessible to pilots and ground crews alike. The pedagogical sophistication embedded in these educational materials facilitated a broad understanding of the system's capabilities and limitations, regardless of varied technical backgrounds. This systematic approach to training ensured that the sophisticated control systems could be utilized to their fullest potential in the heat of combat. A comparative review of different control force reduction methods experimented with during the war reveals why the spring tab approach proved superior. It struck an optimal balance among effectiveness, simplicity in design, reliability under operational conditions, and ease of manufacturing. While other methods, such as aerodynamic balance tabs or other control surface modifications, offered varying degrees of improvement, none matched the reliable performance and straightforward implementation of the spring tab system. This combination of qualities explained its widespread adoption and success, making it a standout example of effective engineering solutions in a complex and demanding wartime environment. Throughout the war, German engineers tested a variety of control surface innovations, ranging from aerodynamic balance tabs to other modifications, in a relentless pursuit of enhancing aircraft maneuverability. Despite these efforts, most alternatives failed to deliver the consistent and reliable performance of the spring tab system, often hampered by complexity, manufacturing difficulties, or lack of durability. The persistent experimentation underscores the significance of the spring tab as not merely a technological breakthrough, but as a carefully optimized solution that managed to outperform the array of competing concepts in the brutal realities of aerial combat. The research into the integration of RVO, reduced visibility operation tabs with hydraulic boost systems, revealed that, although numerous potential solutions existed in theory, only one design, namely the spring tab, possessed the combination of essential characteristics necessary for reliable wartime deployment. This particular solution stood out because it effectively balanced functionality, durability, and ease of implementation under the demanding conditions of combat, making it the only viable choice for operational use during the conflict. Further examination of the recovery and analysis of crashed aircraft provided strong evidence that German technical intelligence services had, by the end of the year 1944, become aware of the existence and basic concept of spring tabs. However, despite this awareness, their understanding of their full significance and strategic potential remained limited for an extended period. This gap in comprehension meant that they failed to develop and implement effective countermeasures swiftly enough to influence the course of the war, ultimately leaving their forces vulnerable to the advantages conferred by these devices. The intelligence reports circulating at that time, which described these devices merely as modified trim tabs, illustrated a fundamental misunderstanding of their true function and critical importance. Such mischaracterizations reflected a significant failure in technical analysis and strategic evaluation, a shortcoming that proved costly to the German military effort. In the final months of the war, this lack of insight and underestimation of the spring tab's capabilities contributed to strategic disadvantages, resulting in substantial losses and missed opportunities to counteract Allied technological advantages.